For over a century, astronomers have tracked a massive spiral galaxy headed straight for our own. The Andromeda galaxy is moving toward the Milky Way at roughly 250,000 miles per hour. A catastrophic stellar crash is expected in roughly 4 billion years, an event predicted to merge these two systems into a single, massive elliptical galaxy. This forecast relies on a specific measurement of distance. Right now, the visible disks of the Milky Way and Andromeda are separated by 2.5 million light-years. Because of that vast distance, astronomers assumed the gap between us was an empty void of intergalactic space, keeping the two systems completely isolated. But new spectroscopic data has revealed a chemical exchange. The physical boundaries of our galaxy are much more expansive and porous than our traditional maps suggested. By analyzing the outermost edges of these galaxies, researchers have found that the collision is already underway. The impending cosmic order is a present-day reality, largely because our previous models of what constitutes a galaxy were too small. When we picture a galaxy, we usually focus on the bright, swirling disk of stars. But that glowing center is only a small fraction of the total structure. Surrounding that stellar disk is the circum-galactic medium, a massive, spherical envelope of gas known as a galactic halo. This is the true outer boundary of a galaxy. This halo is filled with highly ionized gas and heavy elements. Excluding dark matter, this surrounding gas accounts for roughly 70% of a galaxy's normal mass. Because this gas is incredibly rarefied and does not emit visible radiation, it remained hidden from conventional telescopes for decades. To understand our cosmic neighbors and our shared fate, we have to look past the visible stars and map these massive atmospheres. Through an initiative called Project AMIGA, researchers led by Nicholas Lehner used the Hubble Space Telescope to probe the dark regions immediately surrounding Andromeda. This spatial diagram shows the team's methodology. They identified 43 distant quasars, the brilliant cores of active galaxies, positioned far behind Andromeda to act as cosmic flashlights. As the light from these background quasars travels toward Earth, it passes through Andromeda's surrounding gas. By measuring the light that reaches us, scientists can see where specific frequencies are absorbed by the invisible ionized gas. Tracking these absorption signatures across 43 different sightlines allowed the team to map the size and structure of Andromeda's halo pixel by pixel. The data revealed that Andromeda's invisible halo extends 2 million light-years outward from the galaxy's center. This creates an immediate geographical reality. With the two galaxies sitting 2.5 million light-years apart, Andromeda's halo reaches more than halfway to the Milky Way. Because the Milky Way is a similar size, scientists assume it possesses a similarly massive circum-galactic medium expanding outward. The two halos, each spanning roughly 2 million light-years, are already physically overlapping within the 2.5 million light-year gap between us. At this distance, the galactic collision is a silent, invisible chemical exchange. Space-based sensors have recently detected a spike in high-energy oxygen ions in the Milky Way's extreme exosphere, the outermost gaseous layer of our galaxy. These ions carry the specific spectroscopic signature of ancient gas from Andromeda's advancing edge. Our galaxy is actively absorbing this foreign gas. This influx of ionized hydrogen and oxygen atoms creates a physical bridge between the two systems. As this material settles into our galactic environment, it acts as a reservoir of fuel that could spark new star formation along the outer reaches of the Milky Way's disk. The opening stage of our galaxy's merger is a chemical interaction that is actively altering the composition of our galactic exosphere. For decades, we viewed the 2.5 million light-years between the Milky Way and Andromeda as an empty gap. The AMIGA data shows that the intergalactic space separating our two star systems has officially ceased to exist. This region has become a shared cosmic mixing bowl and a physical bridge for high-energy particles traveling between the two galaxies. Tracking these chemical signatures allows us to map the true scale of our neighbors, revealing that cosmic boundaries are far more expansive than previous telescope observations suggested. Humanity is currently living through the opening chapters of Milkomeda, the ultimate cosmic merger.